Hello everyone and welcome back. So today we'll be talking about the electric potential that is created due to a point dipole. Now before we begin talking about the actual electric potential, I think it's useful to define what an actual dipole is, a point dipole. So a point dipole is simply a pair of oppositely charged particles separated by some distance d. So if this is plus q, then this charge over here has to be minus q, and you can let this distance between them be suppose d or 2d depending on how you want to work with a dipole. And while this definition is perfectly sufficient to describe what a dipole actually is, it really doesn't tell you anything about where defining a dipole might actually be useful and why do we actually choose to define such a system, yeah? So the actual physical significance becomes apparent only when you talk about chemical bonding, right? So when let's talk about a regular covalent molecule. Now consider HCl. Okay, so this is hydrogen and this is chlorine. And so the bond between hydrogen and chlorine is actually a covalent bond. It only dissociates into ions in a aqueous solution. So suppose if you've got a bond over here, and the bond is actually formed due to sharing of electrons, right? So there's one electron from hydrogen, there's one electron from chlorine, and chlorine along with that has a lot of valence electrons. Hydrogen doesn't have any other electrons, so we can also denote the valence electrons of chlorine over here, and like this. Now they're visible, yeah. So what actually happens within this particular molecule? We call a molecule such as a polar molecule because chlorine over here actually, due to its high electronegativity, it attracts the shared pair of electrons to itself, such that we can call it to have a partial negative charge, and hydrogen, because the shared pair of electrons has gone away from it, we say that it has a partial positive charge. So effectively what actually happens is that we can say that the center of negative charge is somewhat over here and the center of positive charge is actually over here. And so since there is a difference in the centers of positive and negative charges, an electric potential that is created, and because there's an electric potential, there's also an electric field that's created. And it is due to the separation of these charges that we find it significant to define a point dipole. And so the situation that we have over here is perfectly analogous to the actual definition of a point dipole. So this is how you actually define the dipole, and only then do we study it in physics in this manner. So it's actually useful to begin with it from the chemistry point of view and then go to the physics point of view. Also, yet another thing becomes clear when you study it from the chemistry point of view. For example, when you study for the first time in physics, you see a pair of oppositely charged particles separated by some distance, and instinctively you know that these pair of oppositely charged particles need to attract each other. And so, what's just stopping them from just going into each other and annihilating them each other, right? And so it's a very natural doubt to have because up till now you've always heard that a pair of oppositely charged particles attract each other. So what's just stopping them? And so yet again, when you look at it from the chemistry point of view, you realize that there are a whole lot of intermolecular interaction that are going on. Because there's the repulsion from the electrons, the valence electrons in the chlorine molecule over here, and then these electrons in the valence shell are actually exerting a force of repulsion in the shared pair of electrons, which is preventing the uh, the shared pair of electrons to simply directly go into the chlorine molecule. And so the conclusion that we actually come to over here is that the dipole always exists in a state of equilibrium. That is, the net forces on the dipole that you see over here in the physics case is actually in equilibrium. That's why, even though there's a force of attraction between these molecules over here, there are also various net forces that are actually acting on these positive or negative charges that actually cause them to be in a state of equilibrium. There's no net force, and hence they stay where they are. And so, with that short description out of the way, I think we can finally begin to talk about the electric potential. Oh, by the way, before we begin, again, I forgot to define a very important and meaningful quantity. This quantity or physical quantity is called the electric dipole moment, and it's represented by the symbol P. It's a vector quantity, so we can draw an arrow about there, and it is represented by the magnitude of the charge on either charge, that is either the positive or negative charge, times the distance between them. So it could be QD, and since it's a vector quantity, it also has a direction, and the direction is from the negative to positive charge. So if you have a dipole over here, this is minus Q, this is plus Q. The direction of the dipole movement will be from this to this. And the dipole moment in general is a quantity that depicts the strength of the electric dipole, that is the strength of the electric field that the dipole creates, the strength of the magnitude of the potential that electric dipole creates. So it in general just tells you about how strong a dipole is, you could say. And a point dipole is taken to be the limit as the value of d goes to 0. So this can, suppose if I want to write P ideal is equal to limit as t tends to 0 of qd, and so as t tends to 0 the charge q will actually increase, and so it will remain I mean you could say a finite quantity, and again you could say I cap. So with this definition out of the way again, let's finally begin talking about the electric potential. Alright, so we begin by drawing a diagram for a situation over here. So I'll begin by drawing a point dipole. Now this point dipole has product minus q, plus q, and we will call the center O. And now this can be, say, point A, point B, and the distance between the charges is d. And so this distance turns out to be, I believe, d by 2. This distance would be d by 2 as well. And our aim in this video is to find the electric potential at an arbitrary point P. So this is point P. So this is the point P over here, and the distance from O to P is about r, and this point P is inclined at an angle theta, the dipole over here. And so we can sort of find the distance. The distance from charge plus q can be r1. The distance from charge minus q is r2. And in this case over here, what we're going to assume is that r is much greater than t. Of course, it doesn't look like that is actually the case over here, but that is our assumption, because obviously if I were to draw r to be much greater than d, I could fit everything in this page. But just remember that all our calculations from henceforth actually take into account this fact. And moreover, what we're going to do is we're going to need an expression for r1 and r2 in terms of r, so that we can actually do something. So for that, I'm going to draw a perpendicular from, say, point B over here, and I'm also going to extend this OP over here, and then I'm going to draw a perpendicular from point A to the line as well. So what happens is that I can approximately say that the distance r2 is approximately equal to r plus this extra distance O. I can say, let's let this point be C down here. Hold on, it's not here. So the point down over here is point C, and the point up over here is point D. Alright, so I just said that R2 is approximately equal to R plus this distance OC. But why is that the case, right? So in order to understand that, let's look at a right angled triangle PAC, I believe. So in this triangle, AP is the hypotenuse. If AP is the hypotenuse, then we know that AP cos theta would be the side CP. But we've also assumed that R is much greater than D, right? And in this angle, sine theta, we can also consider sine theta to be approximately equal to D by R. And since D by R is approximately 0, we know that this angle over here, this angle that I've just drawn, let that angle be alpha. That angle alpha is approximately 0. So if I were to write, suppose CP is equal to R2 cos alpha, it turns out that CP is approximately, I'm sorry, I actually just scroll down. CP is approximately equal to R2 itself. And Cp, as we've just found out, is nothing but R plus OC. So we can again write down over here R2 is approximately equal to R plus OC. But what is the value of OC over here, right? Now OC from the figure up here, as we can see, again we can see that there is a right angle triangle over here in triangle, suppose OAC. This is the right angle triangle, and over here d by 2 is the hypotenuse. Alright, so if you look closely in a triangle, suppose a triangle OAC, you can see that the angle theta over here is due to the vertically opposite angles, and cos theta over here would actually be equal to OC, that is what we want, divided by the hypotenuse, that is d by 2. So OC in this case is clearly, if I would write this, it's clearly equal to d by 2 cos theta. And here we cannot use approximation because theta over here is the angle made by the point P with respect to the center of the dipole, and that is not necessarily insignificant. So in conclusion, we can say that R2 is approximately equal to R plus d by 2 cos theta. And a similar analysis on the other side actually shows us that R1 is equal to R minus d by 2 cos theta. Of course, I mean, it just follows a similar procedure, so I've decided to skip it, and you can sort of do it as an exercise if you wish to. But you will find out that R1 is approximately equal to R minus d by 2 cos theta. And so we finally go to actually finding the net potential. Now the V net, you could call it, is the scalar sum or just the algebraic sum of the potential due to the positive charge and the potential due to the negative charge. Because it's a scalar quantity, we can simply add the potentials. And so this would turn out to be Q, because we can take the Q common because they both have the same magnitude of charge. And if I take it in the bracket, this is equal to 1 by R1 minus 1 by R2. Of course, the electric potential due to a point charge is given by Q by 4 pi epsilon naught R. And so we can continue. We can write this as Q by 4 pi epsilon naught R, epsilon naught into 1 by, we can now substitute the values. So this is 1 by 4 by R minus d by 2 cos theta minus 1 by R plus d by 2 cos theta. And with this, we will now go down and expand this further. We will write a Q by 4 pi epsilon naught, and this is R plus d by 2 cos theta minus R plus d by 2 cos theta by R square minus d square by 4 cos square theta. So we can cut the r's over here, and what we will be left with is Q by 4 pi epsilon naught times we have to scroll down over here, times d cos theta. We add the 2 d by 2, so we get a full d by 2, I mean d cos theta, by r square minus d square by 4 cos square theta. Now again, this is the exact value for the potential. This is our final expression, but as you can see, it's not very neat and it looks pretty ugly. So it turns out that we can simplify a lot more using our assumption, that is d is much smaller than r, and since it's much smaller than r, we can approximately consider d square by 4 cos theta to be 0. We can just neglect the quantity. So what we finally come up with is V net is equal to qd cos theta by 4 pi epsilon naught r square. And if you remember, we defined a quantity in the beginning of this video, which I told that would be is indicative of the strength of a particular dipole. This quantity that we said is actually p cos theta, and I mean it's actually p, that is the electric dipole moment. So we'll now substitute this quantity, and we can write this to be equal to p cos theta by 4 pi epsilon naught r square. So this over here is the conventionally used expression for the electric potential due to an electric dipole. and a number of observations. Firstly, instead of the potential dropping off as 1 by r, the potential actually drops off as 1 by r square, which is surprising because for all the other point charge system that you've observed, it's always 1 by r, but because maybe it's a combination of both negative and positive charges, the electric potential drops off much faster. That is, it's similar to the electric field because the electric field also drops off as 1 by r square. Moreover, it is actually dependent on the angle theta that the dipole makes with the point P makes with the dipole, and you can see that when it's facing the positive charge, the value of the potential is actually positive. So when I say facing the positive charge, I mean if I go down over here, and if this is the dipole, so minus q and plus q, and I suppose the point P is somewhere over here, the angle theta is going to be acute, and which means that the potential of this would be positive. But if it, or suppose point P was somewhere over here, then it would be making an obtuse angle, and so theta in that case, cos theta would in that case would be negative, and hence the potential as well would be negative. So what we can further write this as in terms of vectors, that is, we can include a dipole moment vector over here, and we can do a scalar product with the radial unit vector, and this should actually give us when you take the cross product, this should be nothing but p cos theta again by 4 pi epsilon naught r square. So these are basically two equivalent expressions that represent the same quantity, but this is just written in terms of vectors. And of course, the scalar product or the dot product of two vectors gives us a scalar quantity, and since the electric potential is also a scalar quantity, this also checks out. So I think that's going to be it in this video. I hope you learned something new, and thanks for watching.